Well, we want to talk about 2's complement shortcut. How can we take the negative of a 2's complement number in a really quick way? First of all, remember the standard way, which is shown here over here on the left. The standard way is you just take the 1's complement of all the digits and then you add 1. So that means switch 1's and 0's and 0's and 1's and then add 1. There's a shortcut way that might be faster for you. What you do is you start on the right-hand side and you copy the digits down like this until you get to the first 1. And you copy that 1 down as well. But then all the rest of the digits, when you move them down, you also flip them. So in other words, this 0 became a 1, and this 1 became a 0, and that 1 became a 0, and that 0 became a 1. That's the shortcut way to negate a 2's complement number. So let's look at 2's complement and try to understand the arithmetic of 2's complement a little bit better. There's rules for binary addition in 2's complement. 0 plus 0 equals 0, 0 plus 1 equals 1, 1 plus 0 equals 1, and 1 plus 1 equals 0, but you have a carry. In other words, really 2. So if you want to figure out how that goes, let's look at the number 5 and we'll subtract or add a minus 3. So we know that should give us 2. So the number 5 in, oops, don't want that yet. The number 5 in binary is basically given right here in an 8-bit number. And the number minus 3. So let's just add them. And if you add them, you notice, sure enough, you do get 2. That's actually because the way they did this, they started counting, and if you notice, they just started counting with zeros here, 0, 1, 2, keeping going binary all the way up to would be 15 normally, but instead what they did was they said, let's put the positive numbers that go 0 up through 7, we'll make those positive, and then we'll make the place where we break right here between 7 and minus 8, and we'll start from minus 8 and we'll make these guys all negative. Notice that makes the 1, the first bit a 1 on all the negative numbers. And it really makes sense too, because if you take this 0 and you were to subtract this 1, what would you need to do? Well, to subtract it, I'd need to borrow from another digit that doesn't show here. So when I borrowed, I would, have to borrow all the way along. I'd cross that guy out, and all these guys would become 1s, and that's what this is. So if I take that guy right there, there it is. And when I take, 0 minus, this guy right here, I'd end up with this number right here. There would be that 1 that it doesn't show because I've only got 4 digits that would have been crossed out. But anyway, the nice thing about this is, notice that, when you go from minus 8 to minus 7 to minus 6, you're increasing, and also you're increasing when you go from 1000 to 1001 to 1010 and so on in a binary way. So that's why that works. So 2's complement subtraction is really the same as adding the negative number, just like you're used to. And you go in the negative direction, that's that direction to the left. So 2's complement overflow. I don't know if you noticed down here, but if you only have 16 numbers, then you can't make any number bigger than, if you're using negative numbers, the way we're doing, you can't make a number bigger than plus 7 or smaller than minus 8. And so this point right here is where overflows occur. That means where you tried to write a number that was too big for your system, for the number of digits that you have. So let's look at that in more detail here. Overflow, the result doesn't fit in the capacity of the representation. That's what overflow is. Arithmetic logic units are designed to detect overflow. That's because it's an important problem that you don't want to miss that it happened. It's really quite simple. The easiest way to detect it is if the carry in to the most significant bit is different from the carry out from the most significant bit, then an overflow occurred. And generally, overflow is reported as a status bit on the CPU. And carry out is not overflow. It's only if the carry in to the most significant bit is different from the carry out. Let's look at an example. So here we have these two binary numbers, which are really, if you notice, this top one is 38, and this bottom one is minus 19. And if I add those two, I should get 19. And sure enough, notice that this number right here is 1 plus 2 plus, let's see, that would be the 4s, the 8s, and the 16s. So 1 plus 2 plus 16, which is 19. And if you notice the carries, if you add all these things up, let's do it. 0 plus 1 is a 1. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 1 plus 0 plus 1 is a 0 with a carry. 1 plus 0 plus 0 is a 1. No carry. And then 1 plus 1 is a 0 with a carry. 1 plus 1 is 0 with a carry. 1 plus 1 is 0 with a carry. So the carry into the most significant bit, there was a carry and there was a carry out. So there was no overflow in that case. And you can see this is no overflow because this is 38 and you're going back 19. So you only get to 19. You know, that's all of those numbers fit within that's 8 bits. So it'd be plus 127 to minus 128. So everything's all okay there. Let's look at another example. There's the carry in and the carry out, they're the same. Okay, so here's another example. When you do this one right here, this is actually 38 and this is 109. Well, 38 plus 109 is actually bigger than 127. And if you look at the answer you got was minus 109, and that's not 38 plus 109, which is bigger than 127. It's a positive number. So what happens is we overflowed here. So let's look and see what happened to the carries. So if you notice, there was only one carry. Let's see, 0 and 1 is a 1, 1 and 0 is a 1, 0 and 1 is a 1, 0 and 0, let's see, did we do that? 0 and 1 is a 1, 1 and 0 is a 1, 1 and 1 is a 0 with a carry, 1 and 1 is a 0 with a carry, that's a 1, and then 1 and 1 is a 0 with a carry, and 0 and 1, let's see, 1 and 1 is a 0 with a carry. Okay, so there was a carry here. 1 and 0 and 1. That's there is a carry there. There is a carry here, but there's no carry right here. 0 and 0. There was the 1 carry and the 0 and the 0. So there was no carry on the outset, but there's a carry there. So notice that the carry in, there was a different number of carries in than there was a carry in but no carry out. And if there's a carry in and no carry out, it's an overflow. Also, if there's no carry in and a carry out, that's an overflow as well. So you can kind of see how that works there. So this is kind of a handy diagram here I like this wraparound diagram. It really kind of shows you how everything matches. On the outside, we have the binary numbers counting from zeros, 4 zeros, up to 4 ones. And we have the different representations of that. 0 through F, that's the hex representation of those, what we call a nibble. 4 bits is called a nibble. And the base 10 representation is given here in this light orange, or semi-light orange. And then the right here, the 2's complement interpretation of that is shown right here. And notice it's all wraparound, you know. This is a circle. It's a wraparound kind of a deal. So when you overflow, if you take 6 and you add 2 to it, you're going to end up with -8, but you're going to end up with that overflow. Because if you add 6 and 2, you know, you're going to end up right here with 1, 0, 0, 0, and that's a -8. And if you check your carries, the carry in and the carry out won't be the same. There was an overflow there. So this is the area right between the 7 and the -8 where the overflows occur in 2's complement. If you weren't in 2's complement and unsigned, it would be up here, right at 0. So here's a quiz for you. Fill in the boxes with the appropriate arithmetic, and I'll let you work on that.